Hello and welcome everyone to the 17th lecture in this NPTEL course of Electroweak Interactions in the Standard Model of Particle Physics. Today we are going to take up a new topic, and this is the topic of electromagnetism. Alright, so this is something that classical electromagnetism, I am sure that you have taken up in your courses, in your syllabus, in whatever that you are doing. If you are studying physics, you know classical electromagnetism very, very well. If we can get to write the Lagrangian associated with that, equation of motion, what kind of degrees of freedom that you can have, how exactly, what are the polarizations of the photon and so on. So, these are the questions that we are going to take it up, and this is going to be very important and relevant when we actually study quantum electromagnetism. Okay? So, let us get started. Alright, so the first point that we know of electromagnetism is essentially the Maxwell's equation. So, these are the majestic equations, and it was actually one of its first kind of unifying electricity and magnetism together. So, it is once again assumed to be one of the pioneering effort of actually finding an unified theory, because at least it unifies electricity and magnetism. And in the standard model, we will see how this electromagnetism is actually unified with weak interaction, and that is what gives the name of electroweak interactions, which is the topic of this NPTEL course. Okay, so let us get started with the Maxwell's equation. I am going to write them in the vacuum, but please remind yourself that what happens to these equations in different media. Okay, so this is something that we all know. The divergence of E is equal to rho, divergence of B is equal to 0. This is a famous law which actually supposes the absence of magnetic monopole. Say for example, this goes against the name of Gauss's law. On the other hand, you have curl of E is equal to minus del B del P del B del T, the rate of change in the magnetic field, and curl of B is actually J plus del E del T, and this is what is called the Ampere's law, where curl of E is equal to minus del B del T is called Faraday's law, right. So, of course, rho is charge density, J is what is referred to as current density, and you must remember that we are writing all these things in terms of C equal to 1. Now, C is actually 1 by square root of mu naught epsilon naught, right, in the vacuum. Permittivity and permeability, and so basically the point is, with C equal to 1, we also tacitly assume that epsilon 0 mu 0 equal to 1. So, you know this famous story, right, that in order to keep the sanctity of the electromagnetic wave equations, which actually explicitly involves the velocity of light, or 1 by square root of E epsilon naught mu naught, first people ask this question, that what happens, that are our laws of electromagnetism going to change in different kind of coordinate system, inertial frames? And then we came up with this famous assumption of special theory of relativity, that velocity of light actually doesn't change in any inertial frame. So, we restore the electromagnetic equations in all inertial frame in the same way, and so therefore, that gave rise to this Lorentz transformation and so on and so forth. But everything started from kind of finding this Maxwell's equation and to keep its sanctity in different inertial frames. So, that is what I wanted to remind you. And once again, we can see that we can have a continuity equation where J and rho satisfies these above equations, Maxwell's equations, so that divergence of J plus del rho del T is equal to 0, or in a sense, I can definitely convert it to a Lorentz covariant equation, which goes like del mu J mu equal to 0, which says that your current is divergence-less, where you construct the forward current J mu in terms of the charge density rho and the current density J. So, this is pretty similar to what we did before, excepting for the fact that you must remember that the charge density and the current density, these two terms were actually borrowed from electromagnetism itself, right. So, the charge density and current density is essentially to attribute to rho and J, which was later taken up when we were writing the scalar field theory. For that also we defined rho, for that also we tried to define what is J and so on and so forth. So, but this original terminology comes from electromagnetism itself. Nevertheless, let us come back. Now, the point is the divergencelessness of B, del dot B equal to 0, you know that this leads to a very important consequence, and it says that the B can definitely be written in terms of a curl of a quantity, and we usually call it A, that is B is equal to curl of A, and once again E can be, because curl of E is equal to minus del B del T, so this also leads to the fact that it can be written in terms of a gradient of a scalar phi, so with this del A del T. So, therefore, these two important things that we can do here is essentially to write B in terms of curl of A and E in terms of minus gradient of phi minus del A del T basically tells us that we can rewrite all the Maxwell's equation in terms of these two quantities. The scalar potential, you know, phi is usually known as scalar potential, and A is the vector potential. And you can very well say, okay, I can construct a 4 vector potential, let us call it mu, exactly in the similar way that I have the scalar potential as the 0th component or the time component, so to say, and the vector potential A as the next 3 components. Okay. And interestingly, then we can construct something called F mu nu. Now, what this F mu nu is? This F mu nu is basically, you know, we can define it in terms of del mu A nu minus del nu A mu. So, this is what F mu nu is, and if you want to write it in terms of component wise, you know, definitely A has all these seeds of phi and a vector A, which in turn can be written in terms of electric and magnetic fields E and B, and if you write it down in terms of this 4 cross 4 matrix, you will see that this is like 0 minus Ex minus Ey minus Ez, Ex Ey Ez, and so on. So, you try to write it explicitly using all the component notation, and basically this is what is called the field strength tensor. So, this is a tensor, it carries 2 Lorentz indices, and you can also see that if you swap these indices, like F mu nu is equal to minus F nu mu, because then, you know, because of this relative sign that you invoked, there will be a relative sign. So, F mu nu is equal to minus F nu mu, and it has 2 Lorentz index, so to say, mu and nu here. This is an antisymmetric tensor, and this quantity is interesting because if you write an equation of the form del mu F mu nu equal to J nu, this is going to give you the Gauss's law and Ampere's law. All right. So, basically that is why, and on the other hand, if you write the equation like del mu of half epsilon mu nu alpha beta F alpha beta equal to 0, this is going to give you another Gauss's law and Faraday's law. So, what does it mean? It basically means that we have converted the Maxwell's equations in a Lorentz covariant way. I have defined a field strength tensor which is like F mu nu, and from that F mu nu I can find an equation of motion, if you so to say, which can be written either in terms of del mu F mu nu equal to J nu, or del mu of half of epsilon mu nu alpha beta F alpha beta equal to 0. This is going to give me all the Maxwell's equations that we actually started with, right? And so, this is the starting point. So, we have been able to convert everything in terms of this 4 vector potential mu and the field strength tensor that we have defined with respect to it. Now, you can ask this question that what is the corresponding Lagrangian, right? So, if these are the equation of motions, what is the Lagrangian which gives rise to this kind of equations? So, we already have seen that the Euler-Lagrange's equation for the scalar field can be written as del L del phi minus del mu of del L of del mu phi is equal to 0, where phi was actually, you know, sort of the scalar field, and we said that if the Lagrangian depends on the fields and its derivative, then in principle using this Euler-Lagrange's equation we get to the equation of motion, and it follows from the invariance of action or least action principle, so to say. Now, the question that we would like to ask is that what will be the corresponding Lagrangian that we can write for the electromagnetic fields or electromagnetism. So, my answer to this question is that the Lagrangian takes a form like minus 1 by 4 F mu nu. which is like minus 1 by 4 del mu nu minus del nu mu into del mu nu minus del nu mu. So, if you do this matrix multiplication, this roughly comes into half of b square minus e square. Now, what is the rationale of claiming that this is a legitimate Lagrangian to describe electromagnetic fields? So, if this Lagrangian using the Euler-Lagrange's equation of motion gives me back the Maxwell's equation, then I will say that I am happy that this is a legitimate construction of the Lagrangian of electromagnetic fields. So, that is what we are going to check, and we want to see that at least whether it can provide me an equation of the form del beta f beta alpha equal to 0, which is the Maxwell's equation without sources. So, this is something source free Maxwell's equation. So, source free Maxwell's equation मतलब यहाँ पे ये equation में del mu f mu nu equal to j nu को 0 कर देना पड़ेगा. So, del mu f mu nu is equal to 0. That is the Maxwell's equation for the source free case. But basically saying that you do not have a row, so to say. So, let us try to do that. Now, what will be the Euler-Lagrange's equation that you can write for the photon field or the vector field that we defined in terms of mu? Now, just to make sure that I do not confuse about these tensor notations, the Lorentz indices that we actually have, I am going to choose a completely different index. So, I will write this equation in terms of an index alpha. So, I would like to write this Euler-Lagrange's equation in terms of del L del A alpha. Remember, I have nothing but to choose one index associated with the A field, because it has by default it is a vector, it is a 4 vector, right. So, it is a 4 vector with a Lorentz index sitting here. So, there is this A mu, so I must actually adhere to that, there is nothing that I can do. So, the first term, which is equivalent to del L del phi, should be written in terms of del L del alpha. What will be the next term? The next term will be the corresponding derivative like del mu of del L of del mu phi. So, del mu के जाएगा में मैं लिख रहा हूँ del beta. Okay, del beta means essentially del x beta, where beta is another index that I assign. So, what will be there inside the parenthesis? This will be del L of del beta A alpha, correct. So, this is the Euler-Lagrange's equation that will be applicable to basically the electromagnetic field or A mu or A alpha, whatever that you want to say. Now, what is del L del alpha? If you adhere to this Lagrangian, that this is minus 1 by 4 f mu nu, which once you expand in terms of the definition of the field strength tensor, it looks like del mu nu minus del nu mu into del mu nu minus del nu mu. So, what is del L del A alpha? Because you see that it does not have any dependence on the fields by itself. So, this is simply 0. Then the next term will be del of del beta A alpha, right. So, in order to do that, what I have to know first, that what happens to this quantity del of del mu A nu of del beta A alpha, इसका क्या होगा? तो you can clearly see that this will be involving the Kronecker delta. So, this will be like del beta mu and this will be like del alpha nu. Now, suppose I want to find out the same quantity for del nu A mu del beta A alpha. इसका क्या होगा बोलो? This is like the only quantity that you actually will have a non-zero contribution when your nu and beta is the same, right? Beta nu and this is going to be alpha mu. So, this is going to be the index, okay. Alright. So, if you do this del of del nu A mu del of del beta A alpha, then this will be del beta nu del alpha nu. Now, we can also rewrite f mu nu in terms of g mu lambda, g nu sigma, f lambda sigma, and that is g mu lambda, g nu sigma del lambda A sigma minus del sigma A lambda. Now, let us come back to this point, that what happens to del L of you know, del of del beta A alpha. Okay. So, this will be from the definition of the Lagrangian, this is minus 1 by 4 del beta A alpha of f mu nu, and that f mu nu contravariant is replaced by g mu lambda g nu sigma f of lambda sigma, right. So, this derivative del beta A alpha is not definitely going to act on this g mu lambda and g nu sigma. So, what I can do, that I can bring them out, okay. And then this quantity is now, so first you see that you have basically a derivative of, so the first quantity is f mu nu del of del beta A alpha acting on f of lambda sigma. F of lambda sigma क्या था? F of lambda sigma, from this expression we can actually do that this is del lambda A sigma minus del sigma A lambda, right. So, now you see that this is going to be f mu nu. So, first term is, this is delta beta lambda delta alpha sigma minus delta beta sigma delta alpha lambda, okay. From the second term, you know, now the second term is basically the derivative of this term is f lambda sigma del of f mu nu of del beta A alpha. So, once again f mu nu is del mu A nu minus del nu A mu. So, this is the Kronecker delta of beta mu, Kronecker delta alpha nu minus delta beta nu delta alpha mu. Now, you take a look that let us take the first term, say for example this term, that g mu lambda g nu sigma f mu nu डेल्टा बीटा लैम्डा डेल्टा अल्फा सिग्मा, ये टर्म ले लेते हैं. इसका क्या होगा, देखो ये डेल्टा बीटा लैम्डा इज एसेंशियली मेकिंग श्योर दैट बीटा एंड लैम्डा हैज टू बी द सेम क्वांटिटी, और दैट विल इम्पोज हियर दैट दिस लैम्डा must be replaced by beta. So, this g mu lambda becomes g mu beta, and similarly this Kronecker delta of alpha sigma, this basically impose that this sigma on this quantity must be replaced by alpha. So, this becomes g mu alpha. तो g mu beta मतलब क्या है, f mu nu into g mu beta. So, this means that this mu is repeated and summed over. So, this goes up with a index of beta, and similarly here nu is repeated and summed over, and this goes up with a index of alpha. Similarly, if you now look into the second term with this Kronecker delta functions, f mu nu del beta sigma del alpha lambda g mu lambda g nu sigma, this will become once again f of beta lambda. So, you can do this calculation, but the bottom line of the whole thing is that these four quantities that we actually found out, these are nothing but all the same, and these are all 4 beta alpha, and that is amazing. So, this is basically saying that del Lagrangian of del beta A alpha is nothing but minus f beta alpha. So, the bottom line once again is that we are actually going to get the Maxwell's equation, which is like del beta f beta alpha is equal to 0, because the Euler-Lagrange's equation में क्या था, the first term is 0, right, the first term is 0, the second term basically gave you this quantity gave you f of beta alpha is equal to 0. So, together you essentially have del beta f beta alpha equal to 0, and this is nothing but the Maxwell's equations for sourceless cases. Now, you can say that okay, I would like to get not for the source free one, but rather I would like to find out del mu of f nu nu equal to j nu. For that, what you have to do, that you have to rewrite the Lagrangian, and with the canonical kinetic term that we actually wrote, I essentially added here one source term with some interaction J mu mu. Okay. And so basically you see that this is basically my J mu, which is a source term or something with some interaction borrowed in. And then if I do the same exercise which you should do at home, then what you will be able to do, that you will find out that the Euler-Lagrange's equation now will give you del mu of f mu nu is equal to J nu. Okay. So then this is excellent. This works, that we basically write our electromagnetism magnetic Lagrangian with mu, which are the vector fields associated with the electromagnetism in terms of this field strength tensors, and the way that we write is minus 1 by 4 f mu nu. You can ask this question, why this factor of 1 by 4 was there, and the answer was lying in the derivation, just because when you take the derivative you had a factor of 4 coming here, and so that gives you the correct Maxwell's equation for the source free case. So that is why this factor of minus 1 by 4 was actually taken. Okay. So this was the case. Now the point is, usually I am not going right now into the details of the QFT, but basically the point is that when we do the quantum field theory, now this mu is essentially treated as a field. Basically then it is expanded in terms of creation and annihilation operators, and then we actually assign about this creation and annihilation operators will essentially follow a commutation relation, and with that we can show that the Hamiltonian actually can be expressed in terms of those creation and annihilation operators, which basically describes the particle like aspects of that particular field, or rather you can then say this mu is nothing but the photon field. We will actually come to that part a little later. I mean, I will give you a glimpse of how this interpretation of quantization actually occurs. Now let us get into something interesting, and let us talk about something like gauge invariance of the Maxwell's equations. Now what is the gauge invariance of the Maxwell's equation? Gauge invariance, this terminology is basically says that you have some kind of freedom in choosing your fields. What kind of freedom that we can have? Remember that we have two important equations, one which is B is equal to curl of A, and the other which is E is equal to minus gradient of phi minus del A del T, right. So these are the two things that we actually found out, and these two, why we could write this in terms of B is equal to curl of A and E is equal to gradient of phi minus del A del T, just because they will satisfy the Maxwell's equation. So therefore you can always say that B could be written in terms of a vector potential, E could be written in terms of a scalar potential, and then we combine those scalar potential and the vector potential to form the field mu, with respect to which the Lagrangian was written like minus 1 by 4 f mu nu f mu nu. So this was the bottom line. However, there is an interesting point to observe, that B is equal to curl of A and E is equal to minus gradient of phi minus del A del T. This remains unchanged by a transformation if you do, like A going to A prime, which is A minus gradient of chi, and phi goes to phi prime is equal to phi plus del chi del T. If you do that, then basically you see that B and E remains unchanged. How? Let us take the example first for E. E is equal to minus gradient of, I am replacing phi by phi plus del chi del T. Okay. So here I replaced phi plus del chi del T, and del A del T, A is now replaced by this quantity A minus gradient of chi. तो A minus gradient of chi here. तो क्या क्या टर्म आ रहा है, माइनस ग्रेडियंट ऑफ फाई, देन दिस ग्रेडियंट ऑफ डेल काई डेल टी minus del A del T, and then this is actually you can bring the gradient out. So this is plus gradient of del chi del T, and you see that gradient of del chi del T gets cancelled, and you basically have the E intact, which remains minus gradient of phi minus del A del T, right. So this remains intact. Similarly, B is equal to curl of A. Now if you replace A by A minus gradient of chi, you see that this remains curl of A, because we know that curl of gradient of a scalar is equal to 0. And once again, I would like to urge some of you, if you are not familiar with this identity, please prove it. Prove it explicitly why curl of gradient of a scalar is always 0. So, therefore, the bottom line of this whole thing is that I can always write the vector potential A with an additional piece of gradient of chi in it, and the scalar potential with a derivative of that same function, right. So, I can always write A prime is equal to A minus gradient of chi with phi prime equal to phi plus del chi del t. It is important to remember that if you are choosing minus sign here in case of A, then you must choose plus for phi, and vice versa. You may say I will choose A prime equal to A plus gradient of chi, then the phi prime will be phi minus del chi del t. But putting these two things together, I can say that mu, the 4 vector potential or the 4 vector field, whatever that you want to say, that mu goes to mu prime, which is nothing but mu minus del mu chi, correct. So, this is mu minus del mu chi. So, therefore, what you actually have that del mu prime, which will be actually del mu of mu minus del mu chi. So, del mu prime, that becomes del mu minus box of chi. Now, this box is nothing but, you remember, this was del mu. In Cartesian coordinates, it is del 2 del x2 minus del 2 del plus del 2 del y2 plus del 2 del z2 with actually del 2 del t2 minus del 2 del x2 minus del 2 del y2 minus del 2 del z2. Now, I would also like you to check that this Lagrangian, which we actually wrote, Lagrangian which was written as 1 by 4 minus 1 by 4 f mu nu, this actually remains invariant under this transformation that mu goes to mu prime is equal to mu minus del mu chi. This is a very important exercise, and I am actually leaving it for you to do, and this is one of the gauge principles, gauge freedoms of the electromagnetic Lagrangian. Okay. So, I think we are going to stop today, and what we are going to do, that we are going to ask this question, that what are the possible choices of chi that we actually can have, so that chi can be chosen as mu prime equal to mu minus del mu chi. So, this is the question that we would like to deliberate upon in our next lecture. But to remind you once again what we have done, that we have successfully formed one Lagrangian for electromagnetic fields, which is defined now in terms of mu, which you can say it's a 4 vector potential constructed of the scalar potential and the vector potential. But now this is elevated to the form of a field, and this field, when upon quantization, can describe the case of a photon, so to say. And then we saw that the success of the Lagrangian that we constructed is lying in its equation of motion, that when we find the equation of motion, that is actually going to give you the Maxwell's equations. And then we say that there is a interesting freedom which is accessible with the field mu, that whenever mu goes to mu minus del mu chi, first of all, we do not see any change in the definition of the electric and magnetic field, and secondly, the Lagrangian, that actually remains invariant. And we would like to see how this freedom of choosing chi is guiding me to write what kind of, how exactly we can write the equations for A, and what will be the solutions for that. So, that will be done in our next lecture. Stay tuned. Thank you very much.